In this segment, we'll present and give an argument for the energy-time uncertainty relation. And very, very often, certainly I do it when I do modern physics, the Heisenberg uncertainty principle is presented alongside the energy-time uncertainty relation. And I've labeled them a little bit differently. Oftentimes it's called the energy-time uncertainty principle as well. Uh, but we've already seen these, where of course the deltas are the uncertainty in position, uncertainty in momentum, in the Heisenberg principle, and the delta E is the uncertainty in a measurement of the energy, and the uncertainty in the time that measurement was made, or that energy was at, was is given by this relationship. They're often presented together in very similar fashion. But really, the energy-time uncertainty relation is completely different in character, although it is related. Okay? And it kind of boils back down to what we've covered previously in the previous segments. Uh, just recall we have for any Hermitian operator G, the generalized Ehrenfest theorem gives the time evolution of the expectation value is the expectation value of this operator. Again, these are sandwiched in between psi's, is what that means. Uh, and in the usual case, as we've seen, if the operator G that represents some physical observable doesn't explicitly depend on time, then the partial of G with respect to T vanishes and it just reduces to this. And I could certainly use that operator G to in the generalized uncertainty principle. The only difference is I've got the uncertainty or the standard deviation in G squared, standard deviation in H. Just use those two operators is greater than or equal to this quantity of the commutators of G of the commutator of G and H. So we've proven that in general. So we just apply it to the operators G and H, where H is the Hamiltonian of the system. Remember. Yeah? However, in our case, if you take a look at this IH bar, I could bring outside the constant here, and the this commutator that's here, if I multiply through by IH bar, just becomes IH bar equal to GD dt. So the commutator multiply through the IH bar to the other side. I simply replace this commutator with IH bar ddt of the expectation value of G. And the i's go out, so again it's real. I can take the absolute value of both sides, and so h bar over 2 is the absolute value of the time derivative of this expectation value. And if you like, you can write this as the uncertainty in G, whatever that physical variable was, and the uncertainty in the energy measurement is equal to this. So it's just our usual interpretation of the uncertainties, that the standard deviation is a measure of the uncertainty in our measurement. Uh, well, uh, you can do an approximation here for sigma g, the uncertainty in it, and if you like, it's just the time derivative of this thing times delta t. If this quantity g depends on time, then certainly I can take its time derivative, and I know really from the propagation of error formula that the error in G is, if G depends on a parameter T, is just dg dt times the error in T is a propagation of error. So it's really a propagation of error formula. And so I get that relationship from the propagation error, or this one here in terms of the uncertainty in G is this derivative times the uncertainty in the time. And I can replace that on this side over here, usually just via the propagation of error. So I've used propagation of error formula for these uncertainties. G is this, and then from 1, if you look up here, 1, replace the G with this propagation of error formula, where the total error in G is, if G depends on time, is the absolute value of the derivative times the uncertainty or the error in the T measurement, its parameter. Holds very, very well. This really is an approximation, but it holds well provided all of these quantities are small. Delta T is small, for instance, and then delta G is small. Plug that in up here. So this delta G becomes this expression times delta E. And then I've got the absolute value is the same on both sides, and I can cancel it. And then I arrive at the uncertainty relationship for the energy and the time. So it's a little bit different. It requires this propagation of error type assumption in it. And you can give some interpretation in it. And here I've actually done this. Delta T is the time it takes G to change by 1 standard deviation. So if G changes by 1 standard deviation, delta T is the time it takes to change by 1 standard deviation. Then one gets this energy and time uncertainty relationship. Here, delta E is the standard deviation in H, which is the uncertainty in the energy. And delta T is the uncertainty in time, with this caveat that it's the time, delta T is the time it takes delta D to change by 1 standard deviation with that interpretation.